Modern language models use many specialized labels. You may see grouped query attention, mixture of experts, or several kinds of normalization. Under those labels, the same computational unit appears, the transformer block. I'm Mehrdad. In Part 1, we will open that block, follow the residual path through its sublayers, and connect the repeated blocks to next token training. Start with one transformer block and read it from bottom to top. The input is normalized, then attention mixes information across visible token positions. That attention output is added back through a residual connection. Next, another normalization feeds the feed-forward network. Its output is also added back through a residual connection. These steps happen in order: attention first, then the feed-forward network. The residual path carries the running representation forward, and each sublayer contributes an additive update. Attention and the feed-forward network are sublayers, not complete blocks. Modern models often normalize before each sublayer. That is called pre-norm placement. The unit itself is still a transformer block. Now zoom out. Tokens become embeddings, and the same transformer block is applied repeatedly. A final normalization and language model head produce unnormalized scores over the vocabulary. During training, those scores are compared with the correct next token. That is the full forward path: embeddings, repeated blocks, and vocabulary scores. If you are following the course, like the video and subscribe for the later lessons. Attention and the feed-forward network do different jobs. Attention lets one token gather useful context from other visible positions. It mixes information across the sequence. The feed-forward network works on each position separately, using the same learned transformation at every position. A common modern version is gated. It combines a gate path with an expanded path, then projects the result back to the model with. So remember the division of work. Attention mixes across positions, while the feed-forward network transforms each position. Both add their updates through residual connections on the same residual path. Attention can mix information only from positions it is allowed to see. In a decoder-style language model, each position can use itself and earlier tokens, but not future tokens. The causal mask enforces that rule. Before softmax, blocked attention scores are replaced with a very large negative value. Softmax then gives those future positions almost zero weight. In the phrase, "the cat sat on the token after on may use the earlier prefix. It cannot use a token that has not appeared yet. This is a visibility rule inside attention. It is different from the training loss mask we will discuss later. Normalization can appear before or after a sublayer. In post-norm placement, the model runs the sublayer, adds the residual, and then normalizes. In pre-norm placement, it normalizes first, runs the sublayer, and then adds the residual update. Pre-norm keeps a cleaner residual path through many layers, so it became common in modern language models. The normalization itself is often root mean square normalization, usually called RMS norm. Modern blocks also commonly use a gated feed-forward network, and they put position information inside attention instead of a separate absolute position table. Some models add query key normalization or extra normalization steps. These are refinements to the same block, not entirely new architectures. The architecture defines a forward path, but the training objective shapes the weights. For a causal language model, that objective is next token prediction. During training, we provide the correct prefix from the dataset. This method is called teacher forcing. The model predicts the next token at every sequence position in parallel. For example, the cat sat on becomes input, while cat sat on the becomes the shifted target. The language model head produces unnormalized scores over the vocabulary. Softmax converts those scores into probabilities. Cross-entropy gives a larger penalty when the correct next token receives a low probability. We average that loss across valid positions and across the batch. One training signal then updates all layers. There is no separate loss for each transformer block. Chat-supervised fine-tuning, or SFT, often uses the same next token loss with one important change. A training example contains system text, a user message, and an assistant reply. All of those tokens remain in the input because the assistant must read the conversation. But the loss is often enabled only on assistant tokens. This is called completion masking. System and user tokens provide context, but they do not directly contribute to the fine-tuning loss. Do not confuse this with the causal mask. The causal mask controls which positions attention can see. The completion mask controls which positions count toward the training objective. They solve different problems. Now we can compare real model families. BERT uses bidirectional attention, so every token can read the full input sequence. It also uses post-norm placement, learned absolute position embeddings, multi-head attention, and a GLU feed-forward network. GPT-2 keeps the residual transformer structure but changes two important choices. Attention becomes causal, so each position sees only itself and earlier tokens. Normalization also moves before each sublayer. The main shift is therefore visibility and normalization placement, not a replacement of the transformer block. Llama 3 keeps the causal residual structure of GPT-2, but updates several internal choices. Layer norm becomes RMS norm. Learned absolute positions become position encodings inside attention. Multi-head attention becomes grouped query attention, where several query heads share fewer key and value heads. The GLU feed-forward network becomes a gated feed-forward network. These changes improve training stability and reduce key-value memory during generation. The block still performs the same two jobs. Attention mixes information. Then the feed-forward network transforms each position. Llama 4 and Gemma 3 show two different modern recipes. Llama 4 uses grouped query attention and modern position encodings inside attention. Some variants replace the dense feed-forward network with mixture of experts routing. Multimodal tokens can also enter the same sequence. Gemma 3 stays dense, but uses normalization both before and after sublayers. It also adds query key normalization and alternates local attention with periodic global attention. Its feed-forward network uses a different gated activation. The details differ, but both remain sequences of transformer blocks. DeepSeek V3 and Qwen 3 make different choices in attention. DeepSeek uses multi-head latent attention. It compresses key and value information into a smaller latent representation, which can reduce cache cost. Its feed-forward network uses mixture of experts. Qwen 3 stays closer to the Llama recipe. It uses grouped query attention, query key normalization, position encodings inside attention, RMS norm, and a gated feed-forward network. The Qwen family includes both dense and mixture of experts variants. Keep the two choices separate. Attention design is one choice, and the feed-forward design is another. Part 2 opens every model as a wired block. Mixture of experts changes the feed-forward network, not the whole transformer block. A router selects a small set of expert networks for each token. Those experts perform the per-position transformation, and their outputs are combined. Attention remains its own stage. The normalization steps and residual path also remain in place. This expert router is not attention. Attention mixes information across token positions. Expert routing selects which feed-forward parameters process one token. Video 6 will explain that routing in depth. Keep 3 ideas from Part 1. First, a transformer block applies attention, and then a feed-forward network, with residual additions after both. Second, the model repeats that block and trains all layers with next token cross-entropy. Third, model families change visibility, normalization, attention, and feed-forward details without removing the basic unit. Those details change. The transformer block remains. In Part 2, we will open 7 model blocks, from BERT through Qwen 3. After that, Video 5 goes inside attention and explains queries, keys, values, and key-value memory. Subscribe to Multi-Agent Academy and connect with me on LinkedIn. Thank you for learning with me.